If we continue down the column to potassium, we see that the potassium metal is also stored under mineral oil to minimize its reaction with the oxygen in the air. If we remove a piece of potassium metal, we can see that the potassium is coated over with a gray coating of the oxide. As we continue down the column, group 1 metals get softer and softer. The potassium cuts very easily. As we cut through the metal, we expose the shiny metal surface underneath. The potassium is extremely soft. We can easily flatten out the potassium metal. It has a consistency of cream cheese. The potassium is a metal and is an excellent conductor of electricity. If we add a piece of potassium metal to water, we see that it reacts much more rapidly with the water than the sodium. As you go down the column, the ionization energy decreases and the metal reactivity increases. The reaction is very exothermic and the hydrogen that's produced ignites. We can test for the formation of potassium hydroxide by adding phenolphthalein. The solution turns red-purple due to the formation of potassium hydroxide.
This is a demonstration video showing some of the chemical characteristics of sodium metal along with some of the chemical reactions of sodium and sodium-based compounds. Sodium metal is typically stored under mineral oil, as sodium metal would react with the humidity in the atmosphere. And unlike most metals, sodium is relatively soft, so it can be cut with a scalpel, as shown here. You wouldn't be able to cut a block of iron as easily as this. When the sodium metal is cut, you can see a shiny metallic surface is exposed. The shiny surface created will rapidly tarnish in air due to the humidity, then form a dull surface. Since sodium metal is reactive, the first set of experiments we're going to perform, we're only going to use a small amount of sodium metal. The larger pieces of sodium metal we're going to store back under the mineral oil until we're going to experiment with those later. The first chemical reaction we're going to look at is sodium metal reacting with water. We measured the initial pH of the water and found it to be around 6. Now we drop in some sodium metal and immediately you can see a reaction. Once all the sodium metal has reacted, we've measured the pH of the liquid again, and this time it is alkaline, with a pH of 14. This is due to the formation of a solution of sodium hydroxide. Let's put a larger piece in and light the hydrogen. See the characteristic yellow flame of sodium? We'll try an even larger piece towards the end of the video. More sodium metal was reacted with the water to form a stronger solution of sodium hydroxide, and now we're going to have a look at some of the chemical characteristics of sodium hydroxide solution. To start with, we're going to pipette a small amount of our concentrated sodium hydroxide onto some aluminium foil, and you can see a reaction where the sodium hydroxide is reacting with the aluminium to form aluminium aluminate and hydrogen gas. In our next demonstration, we're going to see the chemical reaction between solutions of copper sulfate and concentrated sodium hydroxide. In this demonstration, concentrated sodium hydroxide solution is going to be pipetted into the blue copper sulfate solution. When these solutions meet, you can see a precipitate is formed. This is a double displacement reaction, and the precipitate formed is copper hydroxide. In the next demonstration, we're going to look at the reaction between copper nitrate solution and sodium hydroxide. In this demonstration, concentrated sodium hydroxide solution is going to be pipetted into the blue copper nitrate solution. And when these solutions meet, again we can see a precipitate is formed, and this precipitate is again copper hydroxide. And the double displacement reaction has also formed sodium nitrate, which remains in solution. In the penultimate demonstration, we're going to show the rather gruesome reaction between concentrated sodium hydroxide solution and a raw chicken drumstick. This reaction is shown by immersing a chicken drumstick in the solution or a beaker of concentrated sodium hydroxide solution at around 60 degrees Celsius. After about an hour, when we decant the solution, you can see quite gruesomely that the chicken drumstick has effectively turned into a liquid soap, and all that's left over is a chicken bone. So this illustrates the potentially dangerous nature of sodium hydroxide solution. In our final demonstrations, as promised, we're going to experiment with the larger blocks of sodium metal. And to do this experiment, we ventured outside rather than to conduct this experiment within the workshop. We set the cameras up and chucked a rather large block of sodium metal into a lake of water, and after a few moments we have an upscaled reaction of what we saw in the workshop. Thanks for watching.
We'll go down the column on the periodic table in group 1 and look at sodium. Like the lithium, the sodium is stored in a mineral oil to minimize reaction with the oxygen in the air. If we remove a piece of sodium metal, we notice that it's also coated over with an oxide coating. Group 1 metals become softer as you go down the column. The sodium is much easier to cut than the lithium. As we cut off the oxide layer, we can see the shiny metal underneath. It coats over very rapidly with a layer of oxide. The sodium is a metal and is an excellent conductor of electricity. If we take a piece of the sodium metal and add it to water, we notice a much more rapid reaction with the water. Like lithium, the sodium is less dense in water and floats. The metal moves across the surface, being pushed by the hydrogen gas that is produced. As you go down the column with group 1 metals, the melting point of the metal decreases. The reaction is very exothermic, which causes the sodium metal to melt. The metal contracts into a very compact spherical form. We can again test that hydrogen gas is being produced by this single displacement reaction by trapping the gas and testing its flammability. We can test for the fact that we produce sodium hydroxide by adding phenolphthalein. The phenolphthalein turns a purple-red color due to the presence of the hydroxide ions, indicating the formation of the sodium hydroxide.
sample of metals to check out how they react with water. Don't forget our basic aim, to find out the order of reactivity of these metals. If a metal reacts more vigorously with water, then it is said to be more reactive than the one that doesn't react as much. In general, metals react with water to form metal oxides and hydrogen gas. And if the metal oxide formed is soluble in water, it will dissolve to further form metal hydroxide. So how can we judge the order of reactivity based on their reaction with water? We perform a simple task. First, we take a beaker half filled with cold water and see how the metals react with it. Some of the metals will react with cold water, but most of them won't. Out of those metals which didn't react with cold water, we try to add them to hot water and see how they react. Again, some will react with hot water and some won't. Those that don't react with hot water, we see how they react with steam. And that will kind of give us the order of reactivity. Ones which react easily with cold water are more reactive, and the ones which required steam to react are not as reactive. Metals like sodium or potassium react violently with cold water. In cases of these two metals, the reaction is so violent that the evolved hydrogen immediately catches fire. The equations look like this. This hydrogen catches fire immediately after the reaction. That's how vigorous the reaction is. So we know that sodium and potassium are very reactive. Remember, we're still talking about reaction with cold water. How does calcium react with cold water? Well, calcium does react with cold water, but the reaction is not as violent as what we'd seen with potassium and sodium. The heat is not enough for the hydrogen to catch fire. But what happens is that the calcium starts floating because bubbles of hydrogen gas formed stick to the surface of the metal. And magnesium? Does it react with cold water? No, it doesn't. But magnesium reacts with hot water to form magnesium hydroxide and hydrogen gas. And just like calcium, it starts floating due to the bubbles of hydrogen gas sticking to its surface. The remaining metals we see here don't react with hot or cold water. But aluminium, iron and zinc react with steam to form metal oxide and hydrogen. And the other metals like lead, copper, silver and gold don't react with water at all.